Thank you much. Afternoon, everyone. I know time is short, so I'll give you the short version of this talk. Where's that from? Spaceballs. So today I'm going to talk about doing basically payload automation using Python. Now, the genesis for this is on a program that we support at Northrop Grumman Azusa. We use these things called stored programs, which essentially are just test scripts that are executed by the flight software. They're kind of basic in nature. They could send commands, they could read telemetry. They have some primitive conditional statement logic that you could implement with them. They could also do time delays, and they know about the time. But they're pretty basic, and the issue is that the stored program interpreter and the scripts that they're written in, and you have to compile them. That is all owned by a non-Northrop Grumman entity. So it's very proprietary. Matter of fact, I wanted to show you sort of an example of that, but it's proprietary. So they said no. It's also kind of convoluted, probably why I didn't want you to show the example, because it's sort of readable, but the scripting language has its own peculiarities to it. So if you want to learn how to do stored programming, you have to learn this language. You have to learn how to use the compiler. You have to learn all the features of the compiler. So we figured, we want to do other things. We're getting some new business. We have those businesses areas will need the ability to do payload autonomous commanding. So what is out there? Sort of give you sort of a life of a stored program. Usually they're loaded from ground. Actually, they're always loaded from ground. And then what you do is this is non-volatile memory. And what the operator will do is they will load one or more stored programs into volatile memory right here. So basically they'll say, I want store program X. So they'll send a command to load store program X. And then it's loaded and it's ready to execute. And if it's loaded and your stored program's looking for a specific spacecraft event, it'll trigger on that. Or you can send it to command and say, run. It'll run. And then it goes to completion, and then you have to unload it, and then it kind of goes back and back. We have stored programs that run like every day. So they're looking for a specific spacecraft event. And you can load more of these. On a particular program that we use these for, there are about 10 of them. So we were looking for, like I said, what sort of candidates out there. We don't really want to use a legacy one, but we have some requirements that we need. One is we want it written in some high-level language because, like I said, it's really hard to train the people to this current legacy system. So we don't want, and it's really, really hard to find somebody that's, one, interested in learning this, and two, learning it. So we don't, whatever we picked, it should not require any specialized skill sets. We want to obviously use it without restrictions, and it has to support the core functionalities of our legacy system. It has to do conditional statements, it has to delay statements, you have to read telemetry, you got to send commands. So the genesis of this is, and there's been a lot of talks at this conference already, is a lot of the test scripts are starting to be written in Python. So it's like, okay, so can we, if they're writing test scripts in Python now, can they write stored programs in Python now? And God forbid, we could actually have non-flight software engineers write these things. And that would be good for maintenance. And management loves that, right? Because flight software people are expensive and all that stuff. So we were like, okay, can we use Python? I don't have to give an example. Python, awesome, right? Free, interpreted. Not so awesome for me because I like compilers. It's readable, It's modular, and all the new kids, the cool kids, know how to do this when they graduate and they get CS degrees, which is another topic entirely on that one. So the flight software that we're looking at is written in C++. There actually is an API to launch and use Python with C++ applications. It actually has, the API has a built-in interpreter. You could either do Python strings, or you could actually load a file. And actually, I'm not being quite fair to this API because it has many, many things it could do. And here's the ubiquitous hello world. So Python at H, that's the API that we're including. This initializes the interpreter. This command here, I'll talk about these commands in a sec. This runs a simple Python string. The PI finalize kills the interpreter, and then it just returns 0. That's pretty basic. Here's some of the commands. Like I said, it's very extensive. So if you're interested in this, please go to the API C reference website. It's on my slide. I have a link to it. Besides the ones I talked about, this set program name, this is actually recommended by the API before you actually start the interpreter. It defaults to Python, but they said, well, especially if you're going to load a Python program from a file, you really want to do this first. So my hello world program didn't do this, but they recommend it. Like I said, you can run a string or you can run a file. This clears any references. Not to get too into Python, but everything's modular. Everything's a reference. So this clears it. Finalize, like I said, removes the interpreter. So memory management. So the API uses its own private heap. And this was a bit of a worry because we have statically allocated memory requirements. So if we're going to use this, we understand what's this, how does this heap work? Can we limit it? Does it grow? Does it get dynamic? When we run stored programs every day. So if we start an interpreter and we end the interpreter, is there anything left over? This sort of thing. So this is sort of the things that we're looking at. If you want to pass data between C and Python, the API even acknowledges this. It's kind of inefficient. This doesn't really impact us because I'll show you in a sec how we're going to transfer data between the system and the stored program, Python stored program scripts. But we do want to focus on this to see exactly how limited it is. It does actually allow you to do dynamic allocation, right? Because it's Python, after all. And you could actually do malloc and reloc and free. We're going to prohibit this. And we have no really need for stored programs to do this anyway, because we don't want memory leaks. Exception handling, Python obviously supports exception handling. Our current legacy stored program does not. So this is actually very appealing to us because as you'll see as I go through these slides, one of the concerns is we don't want a error in the stored program to propagate to the flight software. So whatever happens in the stored program stays, and sort of like Vegas. Okay, so some of the constraints that we're going to put on these stored programs, and if we actually use this for our flight system, we're going to stick with this. Like I said, exceptions are very interesting to us. So basically, we'll encapsulate the stored program into a exception block. So if an exception occurs, it will stay within the Python interpreter. Use API functions. One of the things is Python supports multi-threading. We want a deterministic system, and especially if these things are being written by non-flight software engineers, we don't want them to start threads. And there's no reason to do this. So we're going to limit that. Only one stored program could execute at a time. This basically matches the legacy system. Basically, yeah, we're going to have, so the stored program has its own scratch pad memory space. So it does not have access to the whole flight software. It just has its own little sandbox, which it could read. And it will never write, and that's to preserve data integrity. And we want to limit this as a maximum size because that basically, we want to limit the store program writers because they could get a little crazy, and we also want to limit that heap that I was talking about. This is something that's different with the legacy system. I didn't talk about this, but the legacy system only supports store programs that are so big. And so what we do, even though the people who maintain the store program interpreter says don't do this, is we'll have store programs call another store program, which calls another store program, which calls another store program. So we'll like daisy chain these because we have a limited size. So what we want to do is for these Python store programs, we want to find the right ideal size, sort of like the Goldilocks zone, one that is big enough that whatever store program you want to write, you could write, but it doesn't get too crazy. So like I said, one of these we want to do is we want to contain these stored programs because whatever happens to them, we don't want them to propagate to the flight software proper. So I have a picture of this. So when the store program is initiated, it's going to be in its own thread. So the flight software is going to launch a new thread specifically for it. And then when the store program executes, that thread's going to go away. Like I said, each stored program has its own sandbox. So it can't go outside its sandbox. And once the store program is closed, we want it to be dead. So any heap space that was allocated in memory for the interpreter needs to go away, and no other residual issues. So here's sort of what I talked about in graphic form. So they send a command, like I said, the command can come from the ground, or it could have the store program could be just resident in memory waiting for some spacecraft or payload state event to occur. So this is internal or external. The scheduler says, I got a store program I want to launch. It's going to launch its own thread. It's going to execute. The Python's going to execute. It's sharing its space between its little scratch pad area. When it's done, we kill the thread. People thought killed was a little bit too strong. Then it removes it from the scheduler. So command and telemetry. Like I said, these stored programs have to have access to our commands, or basically our database, telemetry database. It's got to support it's got to read our commands, and it's got to know what telemetry monitors that we have. So it's like, how do you do this? So we're doing it through reference tables. So there's this little scratch pad area that I was talking about, and we have a telemetry reference table and a command reference table. So like when the Python store program wants to send a command, it's going to put its command in its command queue, which the command manager is going to pool. It never pushes, it always pulls. So if there's a high priority task that the flight software is doing, then it could decide on its own good time when it's going to actually look at this. The one thing about store programs is it doesn't have to be real time because it's really event driven. So as long as the store program executes when the event within the event timeline, then we're okay. But if the flight software is really busy doing something else, it may take it a bit to go here. And then, like I said, we have a reference table with all of our telemetry monitors. And that's how it reads it. It never reads directly from memory. It's reading a reference table. Timing, it needs to know system time. My system, like all your all systems, we use epoch time. We don't use time of day. So it knows it's epoch time. So it can make decisions. So one of the things is off-nominal processing, right? So what happens if a stored program goes haywire? It's known to happen. Because of this container scheme, it's nice because if something bad happens, we could just kill the thread. But we just don't want to kill the thread. We want to clear all memory that the stored program did. We don't want the interpreter to running. That's something I didn't really mention is when I sort of referenced it when we said that we want one stored program running, we want only one Python interpreter running. We don't want any orphan or zombie interpreters running out there. And you kill the thread. After you do all your cleanup, everything should go away. And the flight software is monitoring. The API does give you a call so the flight software can know exactly the state of the stored program, whether it's running properly or not. So like I said, we wanted to have this demonstration. We are writing flight software for under an IRAD effort for new potential business. And so basically we just wanted to command it for time. I have a better picture of it. So these are two Linux boxes actually. So the flight software is running on a host environment. Like I said, it's really prototype flight software running a prototype stored program thing. The test station is also Linux, and it's running a new Python test script environment. So we got a lot of Python going on here. And they command through the Ethernet. So once we get through this demonstration, then we'll move over to the real flight hardware in a more realistic environment. And this is where I'm being a big tease, because the plan was to finish this year, and life happened, and the real programs got crazy busy, and lowest tail number wins, right? So we weren't able to finish this. We were able to get started. We had stored programs that were written. If I go back, what we're really concentrating on now is this part here. What does this telemetry reference table looks like? What's the best decision for it? Do we use JSON? Do we use XML? Do we use something like that? Also with the commands. And so we were going to work on this next year, hopefully when things get less busy. And yeah. Is there any questions? Yes, sir.
So a couple questions. One is, how do you know that the Python runtime isn't going to make some OS calls that might interfere with flight software somehow, take a semaphore or something like that? And the second question is, dealing with your memory management, does Python have some kind of garbage collector that might come in and start doing things behind your back and taking up the CPU?
Yeah, those are both good questions, and the answer is, I don't know. So that's one of the goals of the demonstration. Is we're really, as most of you guys know, is Python has its own garbage collection. So how does it do that? And how is it going to impact our deterministic requirements for the flight software? So that's the things that we're looking at. But those are very good questions, and they're concerns. Yes, sir.
So we have some experience with Python on RTEMs, and there are other challenges, but there are some smaller Python interpreters, and there's at least one fielded application I know using Python on RTEMs. So
oh, yeah?
it would be really nice there's a small interpreter, which I don't remember the name of, which probably is appropriate to investigate. So
Is it by chance MicroPython?
is that the one I'm thinking of? It sounded like such a trite version of a name, but yeah, that's probably it.
Right version.
That sounded like just something I would have invented off the top of my head, but I think that's it.
Yeah,
But
no.
we had a Google Summer of Codes project at least 5 years ago where a student ported the full Python. There are other issues, like at one point they actually called exit, which is not cool because the RTEM's interpretation on single process is to shut the system down.
Oh, that'd be awesome.
So there were some other assumptions, but MicroPython on RTEMs should be a really good combination for this kind of thing.
Yeah,
You
no,
could-
I'll definitely take a look because I didn't talk about it based on time, but one of our eager new fresh outs got hired. He wanted to write his own. And we were like, let's use this first. If we have to write our own, then we will. But no, I will definitely take a look at that. And I'm going to try the exit thing too, just to see what it does. Because if that'd be hilarious, it happened in orbit. Yeah.
I have two quick questions. The first is you expressed a concern about dynamic memory allocation,
Yes.
but I noticed you were spawning and killing threads dynamically. What went into that decision as opposed to just having a static thread that you could task with running the Python? And the second question is, could you go into more detail about the mechanism that allows flight software to monitor the Python execution?
Like I said, there's API calls. So if you run, like the thread that we're launching could actually just read it at a 40 hertz or whatever hertz rate. The decision to kill and not, instead of just having a static one, we're using VxWorks, and so there's a lot of VxWorks is very powerful. No offense to RTMS for the threads. So, but that's something we're going to take a look at. I mean, if we're monitoring our memory usage over time, and we're going to run this for many days, and we see this growth, then that could definitely affect our decision, and maybe we'll just have like a static store program only thread. Yeah, it's something we're going to take a look at. Any more?
Who set up the MMU to do the protected memory space for just that one thread?
Oh, we did.
So you wrote some custom code for
Yes.
for VxWorks to do that? Because I don't think they have it built in.
No, we have a special sandbox available to us that we use for other programs that won't be talked about here. Any more questions? Thank you. Good discussion. Thank you very much.
Thank you.